Hey, ChemStars, this is Mrs. Vanderwall bringing you the next version of Chapter 4. We're still in the part, or the first section, but this is video number 3. So this is 4.1, number 3. And this is on the heels of what Ms. McCauley did when we said, how do we relate frequency and wavelength? Okay. Well, what is the purpose of chapter 4 right now? If you recall, we ended chapter 3 with the Rutherford solar system model, okay? And we said that was a pretty decent system, but there is a better way to describe it, okay? And that's what we're headed for. So what kind of experiments led to the discovery of the next version of the model, of the atom, okay? And so we're going to describe this photoelectric effect and apply the results to mathematical equations and solve for energy and frequency. So this is our next stop. So I would like you to maybe stop this, go on your place where you're pulling up your videos, and watch the photoelectric effect. This is all about Max Planck and how he came up with a very important relationship between energy and frequency. Now, before you go, I just want to give you a little background about Max Planck. Albert Einstein was at a dinner party one time and he was asked, who's the greatest scientist of all? I mean, that's kind of interesting. What is Albert Einstein's view on this? And he said, Max Planck. Well, why? Because he said, he's quoted, if Max Planck did not discover the relationship between energy and frequency, he would have, Albert Einstein would never have developed his equation, E equals mc squared. Remember, E stood for energy. So Max Planck helped further develop the idea of really nuclear atomic energy, the relationships here, okay? So why don't you pause this and watch the video and come back when you're done. All right, welcome back. Hopefully you took a few notes, all right? And so let's go ahead and kind of recap to make sure you understood what this is. All right, so E stands for energy, and the unit for energy is joules. And joules is like a calorie. So you are trying to lose weight, you want to see how much energy this food has, you look at its calories. Joules are very, very similar, but we use this in science, not in foods, all right? So what is this H? Do you remember the part in the video when Max Planck sent those guys out, say, here, I've thought about this, you go do this experiment, come back and let me know what you get. And they unrolled this long piece of paper with all those zeros in front of it. Do you remember that? Well, what is that number? That is actually called Planck's constant. All right, H is given the term Planck's constant. And that is the value those guys gave to Max Planck. It is written here in scientific notation. Those gentlemen that handed him that value, it was written with all those zeros in front instead, okay? And so what is new? Hey, what's new? That's your frequency. The unit for frequency is 1/2 or hertz. So this is the breakthrough that they needed to relate how do we improve the model of the atom. So how does that work? Well, let's find out. Here's another I can statement. So it says, I can collect and interpret data from atomic spectra, giving evidence that electrons can only exist at certain discrete energy levels and not at energies between these levels. Folks, the certain discrete energy is another way of saying a quantum of energy. All right, so an exact amount of energy levels and nothing in between. All right, so do me a favor. Get me 2 things at your disposal. You'll need 2 things. Get some colored pencils if you have it, or maybe highlighters if that would help. All right, and get out your calculator. You're going to need it a little bit later on, okay? So pause this, grab some either highlighters or colored pencils. I prefer colored pencils if you can, and get your calculator, okay? When you get those things, come on back. All right, welcome back. Hopefully you found it. All right, this is super duper important. I'm going to highlight this. This is huge. All right, can you highlight this? When atoms absorb energy, electrons move into a higher energy level. These electrons then lose energy by emitting light when they return to lower energy levels, all right? So think back to the day we did the flame tests, okay? What did we do? We did a couple things. We either lit those salts, so we absorbed energy by heat, or we turned on those tubes, so we could have given them electrical energy. So when atoms absorb energy, either heat or electrical, the electrons are going to move into a higher energy level. Then what? They're at an excited state. These electrons are going to lose energy by emitting light. We call them photons when they return to a lower energy level. Now, light emitted from atoms consists of a mixture of only what? Specific frequencies. So here's a spectrum. And again, if you have colored pencils, I really wish you could color in these 4 lines. This is a purple line at 410. This is a blue line at 434. This is a teal line, kind of like a greenish blue, at 486 nanometers. And this is a red line over here at 656. So when we looked at the hydrogen spectrum, we saw those lines. All right. What does this have to do with anything? Those lines have specific frequencies. How do I know that? Hey, what's frequency? C over lambda. What's new? C over lambda. So if I know their lambdas, their wavelengths, I know their frequencies. Well, what did Bohr just do? I'm sorry, Bohr, what did Max just do? He said if I know their frequency, I can calculate their exact energies. That's what this is, the exact energy. All right. So these wavelengths in nanometers can be calculated into exact frequencies, and these exact frequencies can be converted into exact energies. Well, what are those energies? When atoms absorb an exact amount of energy, electrons move into higher energy levels. These electrons then lose an exact amount of energy by emitting light when they return to lower energy levels. We'll show you what that means in a minute. All right, here's helium, and for whatever reason, I didn't put the colors in here, so this would be like a purple, this would be like maybe a bluish teal again, this probably is more of a green, this is probably more of a yellow, and then there's your red, okay? And do you remember air? All right, air did not, or I should say sunlight, did not have a specific lines, did they? It was like a whole smear, it was like a rainbow, it was really pretty, wasn't it? Why is that? Well, because the fusion of hydrogen gives off energy of all wavelengths, which means of all frequencies of all energies. All right, so that's why we didn't see any lines. It means that fusion gives off all of that. Okay, let's go to the next page. So what happened? Bohr, Niels Bohr, we even have an element named after him, bohrium, put this all together. He took Max Planck's ideas, E equals h nu, and applied it to the atom. He knew the Rutherford model was not complete because of Max Planck. So he combined those 2 ideas and came up with this. The emission spectrum of hydrogen consists of only specific frequencies. Why? Let's see. So the hydrogen starts off at ground state. That means it's unexcited. This is before you add any energy to the atoms, to the electrons, okay? Did we see any color before we turned on the hydrogen tube? The answer is no, it was colorless. So what happened? You turned the switch on, bink, all right. Now what happened? You got this like pinkish glow, didn't you? All right, what happened? Those electrons are now in what's called an excited state. So what happens, those electrons jump to a higher potential energy, meaning what? They're further away from the nucleus than the ground state. So here's the picture of it. So if you recall Rutherford's solar system model, here's the nucleus. Here's Mars, here's Venus, not Mars, Mercury, here's Venus. Out here would be Earth, right? Same idea. So Rutherford says, here's our very dense nucleus, and the electrons are orbiting the nucleus like they do around the planets of the sun. Well, Bohr said, no, there's more to it than that. Let's apply Max Planck's theory here. What's going on? So when the electron, maybe it's at E1, all right, absorbs energy, it's going to jump to an outer shell, to a higher energy. Then look at this, what happens next? Light is given off by excited atoms as they return to lower states. So the first step is going to go from here to an outer energy shell, number one. How does it relax back down? It's going to go from the outer energy shell back down to its ground state. So it's going to jump back down. Well, how does it lose energy? It gains energy by electricity, or it gains electricity, or gains energy by heat. How does it lose? It releases a photon. So if it goes from E1 to maybe E2, all right, it's going to lose it's going to go back down to E1. It's going to lose a little bit of energy. What if I go from E1 to E3? It's going to lose more energy. All right, so light is given off by excited atoms as they return down to lower energy states. So light is given off in very definite wavelengths. Those are the 4 wavelengths of hydrogen. So we can calculate the wavelength, we can calculate the frequency. Hey, guess what? We can calculate the energy. So watch. We can calculate the energy from E3 to E1. We can calculate the energy from E2 going down to E1. Why? Because they relate to these lines right here. Okay, so let's catch this. Okay, so E equals h nu. Again, energy is equal to h, which is Planck's constant, by frequency. So let's go ahead and do the helium line of 668 nanometers, okay? What's a nanometer? 10 to the negative 9th meters. Remember doing this. So here's meter, 1, 2, 3, that's millimeter, it's not meter. 4, 5, 6, that's micro. 7, 8, 9, that's nano. So nano is 10 to the negative 9th meters. Well, Mrs. Vandal, you're saying that funny. Yes, I know. What's a nano? 10 to the what? Negative 9th meters. All right. So look what happens. If I have 6.68 nanometers, what can I substitute nano for? I can substitute 10 to the negative 9th meters, and now I have done that. So the first step is always making sure we're in meters, okay? Well, why is that so certain? Because I need to calculate frequency next, okay? So what's new? New is C over lambda. Well, Ms. McCauley showed us in the previous film, well, what's C? C is the speed of light, 3.0 times 10 to the 8th meters per second, okay? So now what? I'm going to divide that by lambda. Well, do you see the unit meters per second? That's why we had to convert that to meters. So that what? The meters are going to cancel out, leaving only 1 over second, which is the unit of frequency. So I had to convert to meters. So you have your calculator. I already asked you to get that. Pick it up right now. How did Ms. McCauley tell you to calculate these exponential numbers? Let's find out. Ready? Be careful when using the calculator. Be sure to use the what? The EE, depending if you have a TI, or an EXP button for the exponents. Use caution and parentheses if you insist on using the 10 caret function. I'd rather use the EE button because you're going to make fewer mistakes, I promise. Okay, so let's go back to where we were. So how am I going to calculate frequency? Well, I can go 3.0 EE8 divided by 668 EE negative 9. I'll say it again. 3.0 EE8 divided by 668 EE negative 9. Try that on your own. All right, if you don't have an E button, use the EXP button, but find that. And what do you get? I got this, 4.49 E14. Don't forget to look for your E button because you're going to leave off the exponent otherwise. When you hit your EE or EXP button, make sure your answer, if there's an E or an EXP or whatever on your answer, it means 10 to the, all right? And notice the unit is 1 over seconds, which is the unit for frequency. Well, we're not done yet. Let's go ahead and calculate energy, all right? I know what H is. H is 6.626 times 10 to the negative 34th. And I know what new is. Look at that. I used the same number again. So you might just keep that number in your calculator as long as it's right and multiply by 6.626 e negative 34th. And now what do you get? I get 2.28 e negative 19th. And look at my unit. The seconds and 1/seconds cancels out. So the unit for energy is always joules. Okay, let's go to the next page. All right, I'm not sure if this worked out. I didn't see my counter, so if I'm repeating myself, I apologize. Let's try this one more time. Well, what's E equal to? Equals H nu. H again is 6.626 E negative 34th. And your frequency, I just used the same exact number right here, and I'm going to multiply it by H. So if you still have this number in your calculator, go back and multiply by H, and what do you get? Go ahead and do that. All right, I got 2.28 e negative 19. And notice my units, my seconds and my 1/seconds cancels out. I only have joules left. And there we go. What I decided to do is I'm going to pause this video. I'm going to stop it. And then we'll do a part 4 next. And we'll finish up this section, okay? So don't wait to be great. We'll talk to you later. Bye-bye.